Hi, I'm Helena, and this is my final project where I investigated light fall-off stereo. So in class, we learned about photometric stereo, which can recover depth for Lambertian objects, although in practice, we're also interested in recovering depths for non-Lambertian objects. So another method we can try is one that takes advantage of the inverse square law of light intensity. Basically, it takes advantage of light fall-off distance as a Q. Basically, this law states that how bright an object's surface is inversely proportional to the square of how far away the light is from the object. Because we have this relationship, then it's going to be the case that if we have two different lighting configurations where the only thing we change is how far away this light is from the object in the same direction, then we can relate these two lighting configurations and use that to recover some depth information for the object. So to exploit this light fall distance Q, I used a setup where I took a lot of photos with a fixed camera right here, where the only thing I varied was how far I sort of moved a projector that casts light on the object on the ground along a tape measure. So here's some example images I took where I moved this thing along the tape measure and took a bunch of images. Basically, if I have two of these images, then I can recover pixel-wise depth for every single pixel in the image using the light fall-off distance relationship we described earlier, where if I know the intensity of the object in two different configurations, as well as how far I move the projector between these two configurations, then I can solve for the depth of the pixels in one of these configurations, which is called a local method. So here's some different depth maps I recovered for an apple, for a banana. These numbers just describe, I guess, how close the projector is to the object in terms of some reference depth plane. And also I tested this on some translucent water bottle and a specular mug, so non-Lambertian objects. So I guess overall, I guess something you might notice is that the depth maps you get kind of vary a lot depending on what distances you decide to use for how far away this your projector is placed from the object. This method, I think it actually recovers depth pretty reasonably for Lambertian objects and even non-Lambertian objects, like this apple. And I guess it still doesn't work that well on translucent objects or for specular areas on some parts of this mug. So in that respect, it's not that great. And something else is that this method is also pretty noisy. You can see there's a lot of noise in all of these depth maps. So to try to generate less noisy depths, we can also try to consider more than two images and use that to generate an aggregate depth map. So specifically the depth of a pixel from the closest reference plane, this thing should remain the same across all images. So if we can find a depth that sort of satisfies some depths across a lot of different images, then we have a pretty good depth estimate for this pixel. In practice, this is not really possible due to noise, so we can instead use a series of images to look for pixel-wise depths that sort of minimize the variance of this pixel's depth across all these images. So we can formulate this as a minimization problem where we're interested in an energy function to minimize where this thing sort of punishes a lot of variance for a pixel across all these images, and it also tries to enforce a really smooth solution for a more realistic depth map, where we're basically solving for the depths of every single pixel in our image. And we can do this using conjugate gradient descent. So when I was actually trying this out, I wasn't able to get it to work for large images just because this sort of works with a really, really big matrix where I have the total number of pixels in my image by the total number of pixels in my image, this matrix. So it would crash when I tried to multiply stuff. So I was only able to test this on really small images, 100 by 100 ones. But even for these, you can see that the results that are generated by the global method are definitely a lot smoother and less noisy than the local method variants. So here's some of the depth maps visualized for a section of an umbrella, as well as some depth maps for this section of an apple here, where I actually took processed a bunch of different global method depth maps along different lighting directions, where I placed a light in different places, different directions from the object. And depending on how you orient the light source, you can get actually pretty different shadows or artifacts on your resulting depth map. Yeah, so overall, the global method is definitely less noisy than the local method, but it's also a lot slower. And it gives okay results for non-Lagrangian objects. So it's like a little better than photometric stereo in certain scenes, but it still suffers a lot of the same problems, such as like not really being able to handle shadows or specularities. And it's also pretty volatile, I think, because it's pretty highly dependent on a lot of other things like incident light direction, light distances, etc. Yeah, so that's all I have. Thank you.